Good morning, cadets. In the previous session, in the previous video, we have discussed about the torque experienced by a current carrying coil. Torque experienced by a rectangular loop carrying current placed in a uniform magnetic field. And we got the equation, if you remember, torque 2 is equal to NIA cross B. And here torque is also vector quantity and it is a cross product of NIA and magnetic field B. Here, if you remember, the rectangular coil consisting of n number of turns, you can say n number of turns placed in a strong uniform magnetic field experiences a torque, and we have found out the equation for torque as torque 2 is equal to NIA B sin theta. This is the magnitude of the torque. Here we come across one quantity, that is number of turns into current into area of the coil. This is actually called as magnetic moment of the coil. Magnetic moment denoted by M. It is equal to NIA. So this magnetic moment is also the vector quantity. The magnetic moment is due to the number of turns, current and the area of the coil. The coil may be rectangular. Here we have taken the example of rectangular coil. It just depends on the area. Torque also depends on the area. So the coil may be rectangular, the coil may be a square, a coil may be a circular, it may be of any other shape. It just depends on area of the coil. And this magnetic moment, new quantity which we are defining, is due to the magnetic field that is produced in the coil itself. We have learnt earlier for a circular coil carrying n number of turns, we have learnt what is the magnetic field at the center. Magnetic field at the center is given by mu naught Ni upon 2R. So this magnetic field causes the magnetic moment of the coil. That magnetic moment is calculated as M equal to NIA, where A is the area of the coil. So if you multiply this with the area of the circular coil, in this case, multiplying and dividing by pi r square, then what happens? 1 r cancel. So this can be written as mu naught NIA divided by 2 pi r cube. So that becomes the magnetic field in terms of magnetic moment. So in this NIA, what we get? NIA, this quantity itself is called as magnetic moment of circular coil. So in case of magnetic moment of a rectangular coil, it is same, NIA. So magnetic moment, if it is denoted by NIA, the same torque can be now written as M cross B. That is M cross B, which can be written as MB sin theta into n cap. So this tends to rotate about an axis with some angular velocity omega if the current is in the anticlockwise sense. So this is the magnetic field as we have studied earlier. Uniform magnetic field B, the current I, and it is a coil carrying n number of turns, carrying current I. Coil having n number of turns carrying current I. So magnetic moment of this coil is M equal to NIA. Therefore, it is torque equal to M cross B. Now it is written as MB sin theta, right? Now what is the SI unit? SI unit of magnetic moment. So from this we can very easily write SI unit of magnetic moment as current multiplied by area. Current is measured in ampere and area is measured in meter square. Therefore, ampere meter square becomes the SI unit of magnetic moment. So, the magnetic moment is caused due to the magnetic field that is produced due to the current flowing in this n number of turns of the coil itself. So, this magnetic field and the magnetic moment interacts with the external magnetic field, and as a result of interaction with the external magnetic field, it experiences a torque. That is how we have to understand. It experiences a torque NIA B sin theta. NIA B sin theta, that is NIA cross B. Now, let us solve one numerical problem from the textbook. A 100-ton closely wound circular coil. There is a circular coil of 100 tons. The windings are very closely wound, and the radius of the coil, circular coil, is 10 centimeter. It carries a current of 3.2 amperes. So, I have drawn a circular coil having a n number of turns, that is n equal to 100 turns, carrying current I, you can see current I in the anticlockwise sense, 3.2 amperes, and radius of the coil is 10 centimeter. So, first thing is, what is the field at the center of the coil? What is the field at the center of the coil? You know, if the current is in the anticlockwise sense, the magnetic field is perpendicular to the plane of the coil, which is found out using right hand rule, right? So, the thumb gives you direction of magnetic field due to the current flowing through n number of turns, and magnetic field we have already found out, calculated mu naught Ni upon 2R, where R is the radius of the coil, N is the number of turns, I is the current. So, if you just substitute mu naught 4 pi into 10 to the power of minus 7, N 100 turns, current 3.2 divided by 2 into R, where R is the radius. Radius 10 centimeter can be written as 0.1 meter. So, 0.1 meter. So, if you just cancel 2 ones are 2 2s are, so it becomes 2 pi here. 2 pi into 10 to the power of minus 7 into 100 into 3.2. So, this decimal cancels with this decimal, you are left with 32 here. So, it becomes 32 2s are 64. 64 into 10 to the power of minus 7 plus 2, it becomes 10 to the power of minus 5 Tesla. So, 64 into pi, if you take it, if you multiply this, almost it comes out to be nearly 200. So, 200 into 10 raised to minus 5 becomes 2 into 10 to the power of minus 3 Tesla. This is the magnetic field produced due to the current flowing through a coil consisting of 100 turns carrying current 3.2 amperes with radius 0.1 meter, right. So, we got it as 2 into 10 to the power of minus 3 Tesla. Now, next question is, what is the magnetic moment of this coil? What is the magnetic moment of the coil? So, magnetic field due to the circular coil at the center we have calculated, right. Now, the magnetic moment of the current carrying coil, as we have written magnetic moment as NIA, very easily now it can be calculated. Magnetic moment of the current carrying coil, magnetic moment M vector is equal to NIA vector. It is a vector quantity which acts in the direction of magnetic field of the coil itself, right. So, N equal to 100, current 3.2 into A is the area of circular coil. Area of a circular coil is given by pi r square. Area of circular coil is given by pi r square. You can just write here, area is pi r square. So, if you just substitute pi r square, you will get 100 into 3.2 into pi r square. R is 0.1 into 0.1. So, 3.2 into pi, almost it is taken as 100, 10, it is taken as 10. 3.2 into 3.14, close to 10. So, I have taken it as 10. 10 into 1000 becomes, 10 into 100 becomes 1000. 10 into 100 becomes 1000. 1000 into 0.1 into 0.1. So, that 100 cancels with 2 zeros of this 1000. So, you are left with magnetic moment equal to 10 ampere meter square. So, this is the magnetic moment of the circular coil, magnetic moment of the circular coil. Now, this is first part of the numerical problem. Now, the second part, what happens if the same coil is kept in a strong magnetic field with its area vector having an angle of 30 degree, with an angle of 30 degree with the external magnetic field. What is the torque, right? So, that is the question. Now, let me read the question. This coil is placed in a vertical plane, not 30 degree, it is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with the diameter. A uniform magnetic field of 2 Tesla, uniform magnetic field of 2 Tesla acts, external magnetic field of 2 Tesla acts on the coil. The coil, then initially the axis of the coil is in the same direction as that of the external magnetic field. So, axis of the coil and magnetic field both are in the same direction. What is the torque? Then definitely torque is 0. If the external magnetic field and the coil are in the same direction, means the normal drawn to the coil, gives you the area vector. The area vector and the magnetic field vector, they are in the same direction. Area vector and magnetic field vector, if they are in the same direction, then the angle between the area vector and the magnetic field vector becomes 0. Sin 0 is 0. So, the torque becomes, initial torque becomes 0. If the initial torque is 0, then next, if the same coil is turned through 90 degree with respect to magnetic field, if the coil is turned through 90 degree with respect to magnetic field, then angle between area vector and the magnetic field becomes 90 degree. Then torque tau is equal to mb sin 90, mb sin 90 becomes mb into 1, that itself mb itself. So, it experiences maximum torque. So, those are the things to be calculated. You can see here I am calculating initial torque when plane of the coil and magnetic field are in the plane of the coil is such that its area vector and magnetic field are in the same direction. Area vector and magnetic field, if they are in the same direction, then torque tau is equal to mb sin theta. Then here theta is equal to 0, theta equal to 0. So, it becomes mb sin 0. So, initial torque I will write it as tau I becomes 0. When the same coil is turned through 90 degree, I will draw here, the same coil is turned through 90 degree, here, then magnetic field vector yes, it will be like this. Yes, this is the position of the coil and here is the external magnetic field. The external magnetic field value is given, B is equal to 2 Tesla. B is equal to 2 Tesla. So, what is the value of torque? So, I am calculating the final torque. Final torque initial torque. So, I am writing here final torque. When theta is 90 degree. You can just see here its area vector is perpendicular to the plane of the board. Area vector and magnetic moment vector are in the same direction. Area vector and magnetic moment vector are in the same direction. So, it is perpendicular to magnetic field. So thus theta becomes 90 degree. So tau F is equal to NIA into B into sine 90. Sine 90 becomes 1. Therefore, tau F is equal to NIAB. NIAB. N is 100. Current is, okay, we have already calculated magnetic moment. Magnetic moment already we have calculated 10. So I will directly write it as 10 ampere meter square into magnetic field. The external magnetic field here is 2. So it becomes tau F is equal to 20 Newton meter. Initial torque is 0 Newton meter. Final torque is 20 Newton meter. Now, if it is free to rotate, the next question is, if this coil is free to rotate, what is the angular speed acquired by the coil when it is rotated by 90 degree? The moment of inertia of the coil is given 0.1 kg meter per 0.1 kg meter square. So we will solve that problem. Little bit of mathematics is required. Now you see, question is, what is the angular speed omega of the coil when it is turned through 90 degree? When it is released, suddenly the coil turns due to the torque. So what is the angular speed acquired by the plane of the coil when it is turned through 90 degree? Moment of inertia is given 0.1 kg meter square, 0.1 kg meter square. Moment of inertia, it is written a little artistically I, because I we have used for current. So here I am using I for moment of inertia. So we have learnt in the 11th class, the torque is also given by moment of inertia into the angular acceleration. Moment of inertia I into alpha, where alpha is angular acceleration given by d omega by dt, rate of change of angular speed, This also we have learnt in 11th class. So this is the equation for torque, and torque due to magnetic moment we know mb sin theta, where m is NIA and b is the external magnetic field, theta is the angle of orientation, right? So equating these two, what do you get? If you equate these two, next step will be I alpha equal to mb sin theta. I alpha equal to mb sin theta, right? So if I alpha equal to mb sin theta, you can just see there, I alpha can be written as I into d omega by dt, I into d omega by dt. So this is the torque, that is equal to mb sin theta, equating these two equations. So this can be, next, d omega by dt can be written as, look at this, it can be modified, d omega by dt by just multiplying and dividing by d theta. It becomes d omega by d theta into d theta by dt, where d theta by dt we know angular velocity I omega, angular velocity omega, yes, into d omega by d theta. So substituting this equation here, substituting this in this form, we get I into d theta by dt, I am writing it as omega, into d omega by d theta, d omega by d theta. So I into omega into d omega by d theta equal to mb sin theta, as it is. Now next we are asked to calculate omega. So taking this d theta to the right hand side, we get I omega d omega equal to mb sin theta d theta. Take this d theta to the right hand side, mb sin theta d theta. Now we need to integrate this from 0 to pi by 2, so that we get what is the angular acceleration. So, lower limit will be 0 and upper limit will be pi by 2. So, integrating I omega d omega, we get integration of mb sin theta d theta. So, next what will be the step? Now, carrying out the integration 0 to pi by 2, because it is turned from 0 to pi by 2, I omega d omega equal to right hand side also 0 to pi by 2 mb sin theta d theta. So, here you will get final, we will take the final angular velocity as omega f itself, initial angular velocity will be 0. So, here we can write 0 to omega f, 0 to omega f instead of pi by 2, final omega velocity, angular velocity can be taken as omega f. So, this will be omega square by 2, taking I outside, I omega square by 2 between 0 to omega f, that is left hand side. Right hand side will be cos theta minus cos theta. So, minus mb cos theta between 0 to pi by 2. Integration of sin theta is minus cos theta. So, if you just substitute, we get the result. Simplifying this, we get, so upper limit is omega f, so we get omega f square by 2 and lower limit is 0. So, you can leave that I omega f square upon 2 minus 0 equal to minus mb into cos pi by 2, cos pi by 2, you know cos pi by 2 is 0, minus cos 0, because lower limit is 0, upper limit is pi by 2, lower limit is 0, cos 0 is 1. So, minus of minus becomes plus. Therefore, I omega f square by 2 is equal to minus of minus plus mb. Therefore, we want omega f square is equal to 2 mb by I, 2 mb by I. So, thus finally we get final omega f as square root of 2 mb upon I. This I is not the current, this is moment of inertia, my moment of inertia, everywhere you can just write it I, small artistic I like this, moment of inertia, artistic I. So, this is all artistic I. It is just to identify that this is moment of inertia, not the current, right? Artistic I. I think you will follow it. So, just substitute the value of I here, m and b. We got mb already, 2 into mb. mb value we got, I think mb value is 20, 2 into 20 divided by I is 0.1 kg, meter square, square root of this. So, this becomes, you can see here, 400, 200 into 2, it becomes 400, square root of 400, it becomes 20, square root of 400 becomes 20. So, that is how we get 20 radian per second, or you can just write 20 radian per second. That is the final angular velocity. So, this is a typical problem of calculating the speed with which, the angular speed with which the coil rotates when it is turned from 0 to 90 degree, right. So, this is because of the torque, and the torque is because of interaction between the external magnetic field and the internal magnetic moment of the coil itself. Okay, fine. Now we will solve two more simple examples. So this is another simple example. There is a square coil. There is a square coil consisting of 20 turns carrying current 12 amperes. I have drawn a square coil with 20 turns carrying current 12 amperes. It is placed in the external magnetic field such that the normal drawn to the plane, you can see it, the normal drawn to the plane, this is normal drawn to the plane, makes an angle 30 degree with the magnetic field. So this is the direction of area vector, or this is also direction of magnetic moment. So you are asked to calculate what is the torque experienced by the coil and what is the magnetic moment of the coil. So thus each side is of 10 centimeter. It is a square coil of side 10 centimeter, right? So what is the magnitude of torque experienced by this? What is the magnitude of torque experienced by the coil? So torque experienced by the coil is equal to NIAB sin theta. Magnitude of torque experienced by the coil is NIAB sin theta. So here theta is 30 degree, current is given. So readily you can just substitute 20 turns into 12 ampere current into area. Area is side into side for a square. So 0.1 meter. So because 10 centimeter can be written as 0.1 meter. 0.1 meter into 0.1, that is side into side, into sin 30. Angle between this area vector and the magnetic field is 30. Therefore it becomes sin 30. So next can be written as 0.01. 0.1 into 0.1 is 0.01 into sin 30 is 1 by 2. So you can just cancel 2 with 2 ones are 2 tens are. So 1 0 cancels here. So you are left with 1.2. Right, 1 0 cancels here. So 12 into 0.1. So thus it becomes 1.2 Newton meter. So this is the torque experienced by the coil. If the question is asked what is magnetic moment? Magnetic moment it acts along the direction of the area vector, that is normal drawn to the plane. So magnetic moment M is equal to NIA. Magnetic moment. So we already calculated 20 into 12 into area 0.1 into 0.1. 0.1 into 0.1. This becomes the magnetic moment M. So it becomes 12 2s are 24. 24 into 0.1, that is magnetic moment N becomes 2.4 ampere meter square. 2.4 ampere meter square. So this is how, if you remember the concept and the equation, you can very easily solve the problems. Okay. In the next session, we will study about the current carrying, circular current loop as a magnetic dipole. So there how a circular loop or any other kind of loop acts as a magnet. When the current carrying loop is considered, it has got its own magnetic field at the center, it has got its own magnetic moment. So how it acts as a dipole, that is what we are going to see in the next session. Thank you. Have a nice day. Bye.